welcome to our physical sciences session. My name is Temba. Today we are focusing our attention on energy in chemical changes. We basically want to understand exactly what happens during a chemical change and what exactly is the role of energy in a chemical reaction. Right. Now, in as far as, how energy falls into, the broader chemical change, knowledge area. By now, we know something about, that energy is conserved, in a chemical reaction. But today, we'll look at, some of the aspects with regards to the role of energy. So these are the different, components of chemical change in as far as energy is concerned, but would also use context of chemical reactions in terms of types to understand exactly what exactly happens in as far as energy and chemical changes are concerned. Right. Okay. Now, the big idea or the thought that's going to guide our discussion today is around the fact that what exactly is what energy changes occur in a chemical reaction. And remember, when we talk about a chemical reaction, we're basically talking about a chemical change, right? So the word chemical reaction and chemical change will be used interchangeably to refer to one and the same thing. So the big thinking is what exactly happens in terms of energy in as far as a chemical reaction is concerned, right? Okay. Now, terminology forms a very important part of our our topic. And the moment we start talking about defining as an action verb, we need to familiarize ourselves with the definitions. And this is a lot about remembering what we already know. When we talk about remembering or recall, we think of stating principles, laws, or defining. So those are very, very important action verbs. And our point of reference in as far as definitions are concerned is obviously our examination guidelines. So take note of the keywords that make up a definition. And when you write that definition, go over it once more and try and check, does it really make sense to you? In other words, what we're trying to say is that when you define, not only do you use the keywords in a definition, but those keywords actually need to be used in the correct context. So what are some of the important terms that we'll discuss today? It has to do with bond energy. We'll try and understand what bond energy is all about, okay? Right. Now, what exactly happens in a chemical change? And we know that a chemical change is simply a chemical reaction, okay? Now, we know that atoms or molecules, they need to collide with each other. Suppose, for argument's sake, we've got a reaction between, let's say, magnesium, okay, plus HCl, okay? For us to get a product, these reacting particles must collide with each other, or they must come into contact with each other so that we can form the products. Okay, so the atoms or molecules must collide, but these are atoms of the what? Of the reactants. Okay, so atoms or molecules of the reactants, they need to collide or come into contact with each other. Otherwise, there is no way that we can get the product if these reacting particles or substances do not come into contact with each other. And also, what is important in a chemical reaction is that bonds that exist between the reactants needs to be broken. For argument's sake, if we talk about HCl, for argument's sake, for us to form products, these bonds that are existing between the particles of the reactants must actually be broken apart so that we are able to form new bonds. Okay, once we form new bonds, we can now have new substances. For argument's sake, in this case, we can have new substances like magnesium chloride, okay, let's say plus hydrogen gas. Now, for us to be able to form these products or new substances, we need to form new bonds, but new bonds can be formed only when existing bonds are broken. So these new substances that are formed are actually our products. Okay, so take note of the language there that we actually use or make use of. Right. Now, here's an example of a chemical change that takes place. Now, these are molecules of hydrogen which is actually a diatomic molecule. Also, we've got a diatomic molecule of oxygen. For us to form new substances, these existing bonds must be broken, okay? These are bonds between the molecules that must be broken, right? So these are bonds that we talk of, okay? For us to be able to form new substances, right? So in other words, if we have got water as a product or as a new substance, these new bonds must be formed, okay? So these are our new bonds. So these are some of the, the changes that take place in a reaction, okay? So there are bonds that exist between the products. So these are the new bonds that exist, but these new bonds are actually in the product, okay? And the chemical and physical properties of these products will definitely differ from those of the reactants, right? Okay, and then also, you also need to realize that there is also the role of energy in breaking these bonds. That's the big idea in as far as, a chemical change is concerned. This is something that is not entirely new to us, okay? You can tell that, okay, these new substances actually comprise of, the particles that make up, the reactants. So all those ideas, they must definitely come to mind, right? Okay, so when we talk about bond energy, it's the measurement of the energy either absorbed when bonds are broken or released when new bonds are formed. So when bonds are actually broken, energy is absorbed. That's the main idea. So to break existing bonds in the reactants, so reactants actually absorb energy, right? While when new bonds are formed, energy is released. This is when products are actually formed. So when we say that in a chemical change, new substances are formed, energy is involved in breaking existing bonds, while also energy will be released when new bonds are formed, right? Okay, so that's the whole idea in as far as, the role of energy in a chemical change is concerned. Let's take a short breather before we take our discussion forward. See you after the break. Welcome back to our session. We're still talking about the energy changes that actually take place in a chemical reaction or in a chemical change. We've also come to a point where we understand that there is a lot of energy involvement in as far as a chemical reaction is concerned, because we are saying that for us to form new substances in a chemical change, energy must be absorbed, by the reacting particles to actually break down, the bonds that exist between the reactants. But on the other hand, while we form new substances, new bonds are forged or formed. As that happens, energy is actually released. So there's two sides to it. Actually, there is energy absorption for bond breaking and energy release for bond formation when we form new substances. So in terms of our mind map, we know something about the bond energy in as far as, energy absorption or energy release. So for now, we'll focus our attention on, the energy profiles and, how energy then is involved in as far as a chemical reaction is concerned, right? So what we know is that bond energy, okay, is measured in kilojoules per mole. So this is the SI unit of bond energy, okay? So the change in energy during a chemical reaction is due to bond breaking and bond formation. So we say these two happen subsequent to each other. For us to form new substances, bonds must be broken. So in bond breaking, there is absorption of energy, okay? So energy is absorbed, okay? So there is energy absorption, okay? While during bond formation, there is energy release. So the release of energy is actually coupled to the formation of new bonds. So there is a change in energy in a reaction when reactants are converted to products. So this is what we will talk about in terms of the reaction. Right. Okay. So the change in energy is referred to as the heat of reaction. So what do we mean when we talk about the heat of reaction? We talk about the energy change that takes place in a chemical reaction. So in other words, what we're simply trying to say is that there is a comparison that we need to put in place in as far as amount of energy absorbed when existing bonds were broken versus the amount of energy that was released when new bonds were formed. And when we form new bonds, we're saying that's when we get the products or the new substances, as we'd refer to it. So as a result, the comparison between how much is absorbed versus how much is released gives us what we would think of in terms of the heat of reaction. Right. So think of heat in terms of energy. Right. Okay. So the heat of reaction is a measure of the enthalpy change. So there's what we call the enthalpy change, which is actually the heat of reaction. So when we talk about heat of reaction of a chemical change, we're actually talking about the enthalpy change. Right. Okay. So what is enthalpy? Enthalpy is actually the total energy that reactants and products possess when a chemical change does take place. So when we talk about enthalpy, the symbol for enthalpy is actually capital letter H, so which actually has to do with the heat, right? So if we talk about the change in enthalpy of a reaction, so the change in enthalpy, which is our delta H, that's also, so delta suggests change, okay? So enthalpy change is the heat of reaction. So we can refer to enthalpy change as the heat of the reaction. We're still talking about the same thing, which is actually the amount of energy transferred during a chemical reaction. The word transfer is very, very important because in as far as the law of conservation of energy is concerned, we would recall that the amount of energy in any closed system remains constant. What does it mean? Energy cannot be created or destroyed, but can be, transformed from one form of energy to the other. So in any closed system, the amount of energy remains the same. We don't create energy in a chemical reaction or after the chemical reaction, but we can only convert energy from one form to the other. Right. So when we talk about the change in enthalpy, which is the heat of reaction, so when we refer to heat of reaction, we're actually talking about delta H. Okay, so this is our heat of reaction. Right, so the SI unit again of enthalpy change or change in enthalpy is kilojoule per mole. And when we talk about a mole of a substance, remember we are talking about the amount of matter, the SI unit of quantity of matter. Why? Because a mole of any substance actually contains the same number of particles. Now we know that energy is measured in joules, but what do we mean when we talk about a kilojoule, right? Because 1 kilojoule of energy is equals to 1,000 joules, okay? 1,000 joules of energy, okay? So if we say, for argument's sake, we say it's 200 kilojoules, it's actually the same as, if we talk about 200 kilojoules, for argument's sake, we are talking about 200,000 joules of energy. So if we say 200 kilojoules per mole, for argument's sake, we say 200 kilojoules per mole of substance. We are saying that the amount of energy involved is 200,000 joules per mole of a substance, okay? Because this is the amount of sample of substance that we have, because it contains the same number of particles. So take note of these SI units. They are very, very important, but we would always talk about the kilojoules, right? Now, if we are to determine, for argument's sake, the enthalpy change of any chemical reaction or chemical change is the energy of the product or the enthalpy of product. So this is delta H, which is the enthalpy change, is equals to enthalpy of products, okay, which is final, okay, enthalpy of products, okay, less the enthalpy of reactants. So any change in science is equals to final minus initial. Final we end up with the product, but initially we started with the reactants. So less the enthalpy of reactants. So this is the change that we talk about. So this is our heat of reaction, okay? So the heat of reaction is the same as the enthalpy change, right? So this is in terms of energy, but remember, the big question is what energy changes happen in a chemical reaction, right? Now let's try and use a practical example to actually determine the enthalpy change using the bond energies. So the bond energy, we understand that it is the amount of energy either absorbed when a bond is broken or amount of energy released when a particular bond is formed. So the bond between two hydrogen atoms in a molecule is, the bond energy is 436 kilojoules per mole. So what does this mean? For us to break this bond per mole of this substance, we need 436,000 joules of energy. Similarly, when the same bond is formed, this is the same amount of energy that is actually released, okay? So there is a balanced equation of reaction, very simple reaction, which involves the formation of water molecules from simple elements, hydrogen and oxygen. So what do we know? We know that hydrogen, it's a diatomic molecule of an element, okay? So if we balance this equation, we'll have 2 moles of hydrogen. This is the simplest ratio in which they react, okay? Then we've got a mole of oxygen, okay, to give us 2 of water, okay? Right, we have something like this, right? This is the as we would represent it, okay? So if I've used models there, so this is the same as that, okay? And then this is O2, okay? So you can either move in between the molecules, the models, or the chemical formula. Now, if you look at this balanced equation and we are to determine the amount of energy that was absorbed, okay, to break these bonds. So enthalpy of the reactive products, bond breaking, so the sum of energy, okay, sum of energy for bond breaking, okay, how much energy was absorbed during bond breaking? We are saying it's 2 multiplied by those of hydrogen, which is 436 kilojoules per mole, plus 1 of oxygen, which is 1 of that, which is 495, okay? So to break this, we need 495 kilojoules per mole of this substance, okay? So what does this give us? If we go to our calculator, okay, what do we have? We've got 2 multiplied by 436, okay, plus 495, okay. This gives us 1367, okay? So this is 1367, okay, kilojoules per mole, okay? Right? And then the sum of energy for bond formation, okay? This is the amount of energy actually that is released, right? Is equals to, there's 2, okay? Per molecule of water, there's actually 2 of these. So if we draw a molecule of water, this is what is happening, okay? That's a molecule of water, okay? Now, how many of the oxygen to hydrogen bonds do we have? There's 2 of them. And then there's 2 moles. So it's gonna be 2 multiplied by 2 times, that's 463. 463 kilojoules per mole. So if we also do that calculation, what do we have? We have 2 times 2 times 463, okay? This gives us 1852, okay? So that's 1852 joules, okay? Kilojoules per mole, right? So this is the amount of energy that is released when that is actually formed. So we can talk about the enthalpy change in terms of that, in terms of the amount of energy absorbed for bond breaking. And you realize that the energy that was absorbed is actually less than the energy that was released. So in this chemical change, more energy is actually released than absorbed. So the net change in energy is that ultimately in this chemical reaction, energy is actually released, right? Okay, so if we to actually summarize that, we could say that the enthalpy change of this reaction is equals to 1367, okay, minus amount of energy that was released when bonds were formed, which is 1852, right? So if we to evaluate that, we'll then say 1367, okay, 1367 minus, okay, 1852, okay. So the value is negative 485, okay. So this is enthalpy change is equals to negative 485 kilojoules per mole. All right. So this negative value, what exactly does it tell us? Okay. Now let's go back again and rewind. We are saying that for any chemical change, there is energy absorbed to break existing bond. At the same time, after that, when we form new bonds or new substances, energy is released. So in any chemical reaction, energy is either absorbed or released. Okay, now by comparison, in this type of a chemical change, more was released than absorbed. As a result, the net energy change is that in this example, energy is actually released, but it doesn't necessarily mean that there was no energy absorption. So in a nutshell, what we're simply saying is that the comparison between the amount of energy absorbed to break the existing bond is less than the amount of energy that is actually released when these new bonds are formed. So that's the main idea. So the enthalpy change, we can use it to determine the enthalpy change by using the amount of energy absorbed versus the amount of energy released. So the net, so in total, energy is actually released in this chemical change. Right. So you can use a lot of examples, but we wouldn't have been able to quantify it had we not been given the bond energies. So in this chemical change, we are saying that the heat of this reaction is minus 485 kilojoules. So the negative suggests that more energy is actually released than absorbed. Okay, that's it for now. We shall take a short break. See you after the break. Welcome back to our session. We're still looking into the role of energy in as far as a chemical change or a reaction is concerned. By now we appreciate the fact that in as far as bond energy is concerned, we require a certain amount of energy to break existing bonds within the reacting particles. And while the process of formation of new bonds or new products happens, energy is actually released. So by now, we are familiar with the concept of bond energy, okay, which gives us an indication of the amount of energy required to break a bond, which is the same for the same type of bond, which is released when that new bond is formed. So for now, we'll focus our attention on energy profiles, based on the fact that we want to make a comparison between the total amount of energy absorbed when bonds are broken versus the total amount of energy when bonds are broken. So we'll look at the two types of reactions, which is your exothermic and your endothermic, right? Okay, so the law of conservation of energy is very clear in terms of what happens in a closed system. Okay, so we know that energy cannot be created or destroyed, but energy can be transformed from one form to another. So in a chemical change, when we break bonds, we don't destroy energy. While equally, so when we form new bonds, energy is released, but we are not creating new energy. We're just transferring energy, or transforming rather energy from one form to another. So there are two broad categories of types of reaction. We've got an endothermic reaction in which the net energy is actually, absorbed. More energy is absorbed. So energy is not destroyed when bonds are broken, in a chemical reaction. And also in an exothermic energy reaction, which actually releases energy, we actually do not create energy. But the key term or key word is energy conversion or energy transformation. Right. So the two broad categories of reaction or types of reaction is endothermic, in which here we are saying that more energy is absorbed, right? Is absorbed than released. Okay. So what we're simply trying to say here is that in an endothermic reaction, there is both absorption and release of energy. But in an endothermic reaction, more will actually be absorbed in comparison to what is released when new bonds are formed. And then when we talk about an exothermic reaction, we are saying that more energy is actually released, okay, than absorbed. Okay. So in other words, we are trying to drive the point that in these two types of reaction, there is both the release and absorption. Then it will entirely depend how much we absorbed versus how much is released when new bonds are formed. So if we can look at the energy profiles, which actually show the changes in energy, okay, from when we start with the reactants and we form new substances, which are actually the products. Okay, so all substances, they possess energy according to the kinetic molecular theory. So this is a very, very important point to say that any substance in its very existence, it contains some form of energy. Okay, whatever state it is, it can be a solid, it can be a liquid or a gas. And at the very lowest amount or quantity of energy with the solids, the vibration of these particles of a sample of a solid substance actually suggests that any form of matter does contain some energy. Okay, but then what will then differ is the amount of energy that we require to actually, break those existing bonds, right? So all substances, according to the kinetic molecular theory, they actually have or possess some form of energy. Okay, so then we've got, while talking about energy, for any reaction, we know that energy is absorbed to break bonds. Ne? Energy is absorbed, okay, for bond breaking, all right? Right, so to break bonds based on, and the amount of energy will entirely depend on the bond energy involved, okay? So, and then also energy is released, okay, during bond formation, all right? So this is a very, very important point that we need to always make reference to. Okay, so but then for a reaction to start, there's a certain minimum amount of energy that is required for a reaction to take place, and that minimum amount of energy is called the activation energy. So the symbol E subscript capital letter A suggests that it's for an activation energy. So if, say, for argument's sake, a particular chemical change or reaction requires, let's say, 50 kilojoules of energy for it to start. Okay, so if we supply that reaction with 40 kilojoules, it certainly means that the reaction will not take place. Why? Because the minimum or the threshold that is actually required is not sufficient based on what is supplied. So anything beyond or equal to or greater than 50 kilojoules of energy will actually start that reaction. So that's the emphasis is on the minimum, which is actually the threshold, right? So the SI unit of activation energy is kilojoules per mole, right? So if you look at the energy profile for an endothermic reaction, you'd realize that the reactants, which are, are at a particular energy level. So this is the energy level of the reactants. So we have agreed that according to the kinetic molecular theory, all substances possess some form of energy. So for this reaction to take place, we actually need to supply energy to break bonds, okay? So if you think of it, this is the minimum energy that is required for this reaction to take place. So that's the amount of energy that is absorbed. So this is what is absorbed, okay, the minimum. It can be this or more for this reaction to take place. So once these reactants absorb energy, when they reach to a certain stage where now they are able to start forming, the products or the new substance, we have got what is called an activated complex. So this is an intermediate stage between reactants and products. At that time, we are saying that the existing bonds are quickly being broken, and at the same time, we are starting to form new substances. And as we form new substances, the energy in that system actually starts to decrease. Why? Because as we form new substances or new bonds, energy is released. That's why there is a drop in energy. Okay, so the absorption in this case is coupled to energy from the surroundings, being supplied to the reaction. That's why there is an increase in the energy of the system. Okay, so while the new bonds are being formed, there is a drop in energy, all right? So the minimum that is required for this reaction to take place is our activation energy. That's our activation energy. So this interval of energy represents the minimum, okay? So this is what is absorbed, okay, in terms of energy, and then this is what is released, okay? Then we are able to say in an endothermic reaction, more energy is absorbed than what is released, okay? Right, and then that's the, the profile. And then when it comes to the activated complex, we are talking about that unstable intermediate state between the reactants and the products. So what is actually happening when we reach that stage, which we refer to as the activated complex? We are in, halfway in between, the two processes of bond breaking and bond formation are beginning to occur. So we are having these reactants, they are, the existing bonds are being broken, while at the same time, we have got new bonds being formed. And remember, when we break bonds, energy is absorbed. So we may supply energy from external energy, in the form of heat, to break the bonds. Then when immediately we start forming new substances, the energy is released. That's why the profile shows a drop in energy. And then that's why we say at the end of the day, when new bonds are formed, energy is actually released to the environment, right? So the activated complex is that intermediate state between reactants and the product. And we get to understand the role of energy in as far as, a chemical change is concerned. So if we talk about, for argument's sake, in the reaction between hydrogen molecules and oxygen molecules to form water molecules. Okay, so between at that activated complex state, we have got a scenario like this where we are starting to form new bonds while the old bonds have been broken. So we are almost there in terms of forming the product. So this is how you'd want to think of, the activated complex. So it's that intermediate state, right? Okay, so in as far as this endothermic reaction, we are saying that the amount of energy absorbed, let's say for argument's sake, this is 50 kilojoules per mole, okay? And then that's, let's say 90 kilojoules. Now, the amount of energy absorbed is the interval between 50 and 90, which is actually the minimum, which is our activation energy. So our activation energy in this case is actually equals to 40 kilojoules per mole, right? That's the minimum, okay? And then we are saying that these reactants are at an energy level of 50 kilojoules per mole, while the activated complex is 90. So the difference in that gives us the activation energy. And then we know that 40 was absorbed, amount of energy absorbed, okay? So the energy absorbed in this case is equals to, we know it's 40 kilojoules per mole as an example. All right, and then how much is released? From 90, let's say this is 60 kilojoules for argument's sake. So the products are at that energy level. So energy released, right? is equals to, we have released from 90 to 60, we have released 30 kilojoules per mole. So what are we saying here? We are saying that more energy is absorbed than released. Hence, we would refer to this as an endothermic reaction. So at the same time, we are saying that the products are at a higher energy level than the reactants. That's why we are saying more was absorbed than released. Right. So in an endothermic reaction, in a nutshell, at the start of the reaction, energy is absorbed like in any other reaction, and the energy of the system increases. And then bond breaking, which takes place as a result, results in the new bonds being formed. And while we form new bonds, energy is released, okay? So the release of energy is coupled by formation of new bonds to the surroundings. That's why there is a decrease in the energy of the system. Okay, now we're just trying to explain the profile. So in an endothermic reaction, more energy is released than absorbed. This is what we take home. Now, at the end of the day, we're saying that the enthalpy change is positive when more is absorbed than released, right? So that's as far as the endothermic reaction is concerned, that in terms of energy, there is more energy by comparison that is absorbed than what is released. So for now, we'll take a short breather. When we come back, we'll take more discussions on, the other type of reactions in as far as energy is concerned. Let's take a short break for now. Welcome back to our session. We're still talking about the energy in as far as chemical reactions are concerned. By now we are familiar with the energy changes that take place in an endothermic reaction. Now we want to focus our attention on the exothermic reaction, which is the second category of the types of reaction in as far as energy is involved. Right. Now, in as far as an endothermic reaction is concerned, we are saying that more energy is actually, released than absorbed. So, if we talk of an exothermic reaction, that there is more energy that is released to the surrounding than absorbed. So that's by comparison. And then we're saying the enthalpy change, which is the heat of reaction, right? So remember, enthalpy change is the heat of reaction. In an endothermic reaction will always be a negative value. So a negative enthalpy change suggests that the reaction is actually exothermic. Okay, so in other words, if more energy is released than absorbed, it says to us that the products will be at a comparatively lower energy level than the reactants. Right. So in as far as the profile of an exothermic reaction, we realize that immediately that the products are actually at a lower energy level than the reactants. Okay, and if you look at the amount of energy released, okay, that's as much energy that is released versus the amount of energy that is actually absorbed. So we can safely say that more energy is released than absorbed. So if we say the enthalpy change in this reaction is equals to energy of products, right, less the energy of the reactants, we immediately realize that the enthalpy change will be a negative value, okay, will be less than 0 because these products are at a lower energy, okay? But that has nothing to do with, the activation energy. So it can have even lower or higher activation energy, it doesn't matter, but by comparison, more is released than absorbed, right? So then we've got certain types of reactions that are spontaneous. What do we mean when we say a reaction is spontaneous? This is the type of reaction that actually requires very little amount of energy for it to take place. But by now we know that for a reaction to take place, we need to break bonds. So if a particular type of a reaction requires very little energy, which means that this reaction can take place at a very low temperature, we would say that reaction is actually spontaneous. So this reaction will actually occur, at room temperature. So if the amount of energy that it requires is very low, then that reaction is spontaneous. Right. So then on the other end, we have got non-spontaneous reaction. So these reactions will only occur if we raise the temperature above say for argument's sake, room temperature. So these actually require a comparatively higher amount of energy for them to actually take place, whether they are endothermic or exothermic. And then let's look at something that's very interesting in as far as, you know, the minimum amount of energy required for a reaction to take place. We've got a catalyst. A catalyst is actually a substance, okay, that we add onto a reaction, so that the reaction takes place very, very fast. So what a catalyst is actually a chemical substance that is involved in a chemical reaction but is not used up. So the role of the catalyst is actually to lower the activation energy. So if we have a catalyzed reaction, what we're actually saying is that we have added a chemical substance that will actually provide an alternative pathway for that same reaction to take place, you know. But this catalyst does not get used up. So the amount of catalyst before and after the chemical change actually remains the same. But what it essentially does, it lowers the activation energy so that the reaction takes place, you know, much quicker or at a higher rate, right? So what it does, it lowers the activation energy. So if we were to focus our attention, suppose this is the path for the catalyzed reaction, okay? Uncatalyzed rather, okay? So if we introduce a catalyst, now this is the activated complex, okay? Obviously, in the uncatalyzed reaction, there is greater amount of activation energy, okay? But then if we introduce a catalyst, the energy of the activation complex is comparatively lower, okay? But realize that the catalyst does not affect the energy of reactants or the products. That's very, very important, right? Okay, now here is a question. We want to examine an energy profile for a chemical reaction that is represented by this hypothetical reaction where A reacts with B to give us AB, okay? Right, it's a chemical change. And then the first question, before we look at the question, here is the energy profile of this particular hypothetical reaction. Remember, it's A plus B to give us what? AB. So we are reading this or interpreting it from our left to our right. So A and B are our reactants, while AB is our product. So there are given values there on the vertical axis versus the reaction progress or reaction course, right? Okay. Now the first question says, calculate the activation energy for this reaction. So what are we looking for here? We're looking for activation energy. Okay, what is activation energy? Is the minimum amount of energy required for a reaction to take place. So the reactants are at an energy of 225 kilojoules per mole. So this interval to the activation complex actually represents our activation energy. So that interval 240 minus 225, it's actually 240 kilojoules. If we can just correct that value, it's actually 540, right? Okay, it's 540 minus 225, okay? Because we are looking at the amount of energy that was absorbed to break new bonds so that we reach the activation complex. That value is equals to 315 kilojoules per mole. So we need to be able to identify in this profile what represents the activation complex and then do the maths after that. So this is the minimum energy that is required for this particular reaction to take place. Right. Moving along, now we want to identify the energy of the activation complex. Okay, first of all, if we go to our profile, the highest, after supplying that minimum energy for this reaction to take place, we need to identify our activation complex. So this is our activation complex, right? Which has to do with the minimum energy that needs to be supplied for this hypothetical reaction to take place. So the amount of energy that this activation complex it has is actually 540 kilojoules per mole. Right. And then furthermore, we want to calculate the energy released. Remember, when energy is released in a chemical change, the energy of the system drops because the energy is released to the surroundings. So from that energy level, right, to that energy level, when we form the product. This has to do with the energy release. So the difference in this case is actually 540, okay, less 100, okay, which gives us 440 kilojoules per mole, right? Okay, so that's straightforward. That's why there's that drop in the energy in as far as the profile is concerned. Okay, and then the enthalpy change of the reaction. Enthalpy change of a reaction is energy of the product, okay, less the energy of the reactants. Okay, that's what we know. So we read it off from the graph. The products are at 100 kilojoules per mole, less the energy of the reactants, which is 225. Okay, so when we do that difference, it would give us negative 125 kilojoule per mole. Now, this is the enthalpy or the heat of reaction. So this is a negative. What does that tell us about this type of reaction? Which takes us to the next question. So there is a negative enthalpy change in this reaction, which is less than 0, meaning that this is typically an exothermic reaction, right? And then last but not least, if we are to add a catalyst to this reaction, what effect will a catalyst have on this reaction? We know that a catalyst actually provides an alternative pathway with a lower activation energy, right? So if that's the case, so if the blue profile represents the catalyzed reaction, you know that the activation energy will be lower. But what are the options that are given from the multiple choice? Adding a catalyst change from spontaneous to non-spontaneous? Definitely not, okay? Because whether the reaction is spontaneous or not, a catalyst just lowers the activation energy. If it lowers the activation energy, it means the energy of the activated complex becomes lower, okay? That's a change, okay? But the energy of the products, no, the enthalpy change of the reaction is actually not affected. So from 540, we would have a value that is actually less than 540. Right. So that's as far as, you know, the types of reaction and the, you know, how energy is actually involved. So from this, we need to do as much practice as we possibly can so that we can actually be more comfortable around these energy profiles and the, you know, the calculations that go with it. Okay. For now, I think we shall, because that's the time we had for today, we'll call it a day. Bye-bye for now.